A tornado is a violently rotating column of air that is in contact with both the surface of the Earth and a cumulonimbus cloud or, in rare cases, the base of a cumulus cloud. The windstorm is often referred to as a twister, whirlwind, or cyclone, although the word cyclone is used in meteorology to name a weather system with a low-pressure area in the center around which, from an observer looking down toward the surface of the Earth, winds blow counterclockwise in the northern hemisphere and clockwise in the southern. Tornadoes come in many shapes and sizes, and they are often visible in the form of a condensation funnel originating from the base of a cumulonimbus cloud, with a cloud of rotating debris and dust beneath it. Most tornadoes have wind speeds less than 110 miles per hour, 180 km per hour, are about 250 feet, 80 m, across, and travel a few miles, several kilometers before dissipating. The most extreme tornadoes can attain wind speeds of more than 300 miles per hour, 480 kilometers per hour, are more than 2 miles 3 km in diameter, and stay on the ground for dozens of miles, more than 100 km. Various types of tornadoes include the multiple vortex tornado, landspout, and waterspout. Waterspouts are characterized by a spiraling funnel-shaped wind current connecting to a large cumulus or cumulonimbus cloud. They are generally classified as non-supercellular tornadoes that develop over bodies of water, but there is disagreement over whether to classify them as true tornadoes. These spiraling columns of air frequently develop in tropical areas close to the equator and are less common at high latitudes. Other tornado-like phenomena that exist in nature include the gustnado, dust devil, fire whirl, and steam devil. Tornadoes occur most frequently in North America, particularly in central and southeastern regions of the United States, colloquially known as Tornado Alley. Southern Africa, northwestern and southeast Europe, western and southeastern Australia, New Zealand, Bangladesh, and adjacent eastern India, and southeastern South America. Tornadoes can be detected before or as they occur through the use of pulse Doppler radar by recognizing patterns in velocity and reflectivity data, such as hook echoes or debris balls. As well as through the efforts of storm spotters. There are several scales for rating the strength of tornadoes. The Fujita scale rates tornadoes by damage caused and has been replaced in some countries by the updated enhanced Fujita scale. An F0 or F0 tornado, the weakest category, damages trees, but not substantial structures. An F5 or F5 tornado, the strongest category, rips buildings off their foundations and can deform large skyscrapers. The similar Toro scale ranges from T0 for extremely weak tornadoes to T11 for the most powerful known tornadoes. Doppler radar data, photogrammetry, and ground swirl patterns trochoidal marks may also be analyzed to determine intensity and assign a rating. Tornado has no funnel cloud, however, the rotating dust cloud indicates that strong winds are occurring at the surface, and thus it is a true tornado. A tornado is not necessarily visible. The intense low pressure caused by the high wind speeds and rapid rotation due to cyclostrophic balance usually cause water vapor in the air to condense into cloud droplets due to adiabatic cooling. This results in the formation of a visible funnel cloud or condensation funnel. There is some disagreement over the definition of a funnel cloud and a condensation funnel. According to the Glossary of Meteorology, a funnel cloud is any rotating cloud pendant from a cumulus or cumulonimbus, and thus most tornadoes are included under this definition. Among many meteorologists, the funnel cloud term is strictly defined as a rotating cloud which is not associated with strong winds at the surface, and condensation funnel is a broad term for any rotating cloud below a cumuliform cloud. Tornadoes often begin as funnel clouds with no associated strong winds at the surface, and not all funnel clouds evolve into tornadoes. Most tornadoes produce strong winds at the surface while the visible funnel is still above the ground, so it is difficult to discern the difference between a funnel cloud and a tornado from a distance. Occasionally, a single storm will produce more than one tornado, either simultaneously or in succession. Multiple tornadoes produced by the same storm cell are referred to as a tornado family. Several tornadoes are sometimes spawned from the same large-scale storm system. If there is no break in activity, this is considered a tornado outbreak, although the term tornado outbreak has various definitions. A period of several successive days with tornado outbreaks in the same general area spawned by multiple weather systems is a tornado outbreak sequence, occasionally called an extended tornado outbreak. Most tornadoes take on the appearance of a narrow funnel, a few hundred yards, meters, across, with a small cloud of debris near the ground. Tornadoes may be obscured completely by rain or dust. These tornadoes are especially dangerous, as even experienced meteorologists might not see them. Tornadoes can appear in many shapes and sizes. Small, relatively weak landspouts may be visible only as a small swirl of dust on the ground. Although the condensation funnel may not extend all the way to the ground. If associated surface winds are greater than 40 miles per hour or 64 km per hour, the circulation is considered a tornado. A tornado with a nearly cylindrical profile and relative low height is sometimes referred to as a stovepipe tornado. Large tornadoes which appear at least as wide as their cloud-to-ground height can look like large wedges stuck into the ground, and so are known as wedge tornadoes or wedges. The stovepipe classification is also used for this type of tornado if it otherwise fits that profile. A wedge can be so wide that it appears to be a block of dark clouds, wider than the distance from the cloud base to the ground. Even experienced storm observers may not be able to tell the difference between a low-hanging cloud and a wedge tornado from a distance. Many, but not all major tornadoes are wedges. A rope tornado in its dissipating stage, found near Tecumseh, Oklahoma. Tornadoes in the dissipating stage can resemble narrow tubes or ropes, and often curl or twist into complex shapes. These tornadoes are said to be roping out, or becoming a rope tornado. When they rope out, the length of their funnel increases, which forces the winds within the funnel to weaken due to conservation of angular momentum. Multiple vortex tornadoes can appear as a family of swirls circling a common center, or they may be completely obscured by condensation, dust, and debris, appearing to be a single funnel. In the United States, tornadoes are around 500 feet or 150 meters across on average and travel on the ground for 5 miles or 8.0 kilometer. However, there is a wide range of tornado sizes. Weak tornadoes, or strong yet dissipating tornadoes, can be exceedingly narrow, sometimes only a few feet or couple meters across. One tornado was reported to have a damage path only 7 feet or 2.1 meter long. On the other end of the spectrum, wedge tornadoes can have a damage path a mile 1.6 kilometer wide or more. A tornado that affected Hallam, Nebraska on last May 22, 2004, was up to 2.5 miles or 4.0 kilometer wide at the ground, and a tornado in El Reno, Oklahoma, last May 31, 2013 was approximately 2.6 miles or 4.2 kilometer wide, the widest on record. In terms of path length, the tri-state tornado, which affected parts of Missouri, Illinois, and Indiana last March 18, 1925, was on the ground continuously for 219 miles or 352 kilometer. Many tornadoes which appear to have path lengths of 100 miles or 160 kilometer or longer are composed of a family of tornadoes which have formed in quick succession. However, there is no substantial evidence that this occurred in the case of the tri-state tornado. In fact, modern reanalysis of the path suggests that the tornado may have begun 15 miles or 24 kilometers further west than previously thought. Tornadoes can have a wide range of colors, depending on the environment in which they form. Those that form in dry environments can be nearly invisible, marked only by swirling debris at the base of the funnel. Condensation funnels that pick up little or no debris can be gray to white. While traveling over a body of water, as a waterspout, tornadoes can turn white or even blue. Slow-moving funnels, which ingest a considerable amount of debris and dirt, are usually darker, taking on the color of debris. Tornadoes in the Great Plains can turn red because of the reddish tint of the soil, and tornadoes in mountainous areas can travel over snow-covered ground, turning white. Lighting conditions are a major factor in the appearance of a tornado. A tornado which is backlit viewed with the sun behind it appears very dark. The same tornado, viewed with the sun at the observer's back, may appear gray or brilliant white. Tornadoes which occur near the time of sunset can be many different colors, appearing in hues of yellow, orange, and pink. Dust kicked up by the winds of the parent thunderstorm, heavy rain, and hail, and the darkness of night are all factors that can reduce the visibility of tornadoes. Tornadoes occurring in these conditions are especially dangerous, since only weather radar observations, or possibly the sound of an approaching tornado, serve as any warning to those in the storm's path. Most significant tornadoes form under the storm's updraft base, which is rain-free, making them visible. Also, most tornadoes occur in the late afternoon, when the bright sun can penetrate even the thickest clouds. Nighttime tornadoes are often illuminated by frequent lightning. There is mounting evidence, including Doppler on wheels mobile radar images and eyewitness accounts, that most tornadoes have a clear, calm center with extremely low pressure, akin to the eye of tropical cyclones. Lightning is said to be the source of illumination for those who claim to have seen the interior of a tornado. Tornadoes normally rotate cyclonically when viewed from above. This is counterclockwise in the northern hemisphere and clockwise in the southern. While large-scale storms always rotate cyclonically due to the Coriolis effect, thunderstorms and tornadoes are so small that the direct influence of the Coriolis effect is unimportant, as indicated by their large Rossby numbers. Supercells and tornadoes rotate cyclonically in numerical simulations even when the Coriolis effect is neglected. Low-level mesocyclones and tornadoes owe their rotation to complex processes within the supercell and ambient environment. Approximately 1% of tornadoes rotate in an anticyclonic direction in the northern hemisphere. Typically, systems as weak as landspouts and gustnados can rotate anticyclonically, and usually only those which form on the anticyclonic shear side of the descending rear flank downdraft in a cyclonic supercell. On rare occasions, anticyclonic tornadoes form in association with the meso-anticyclone of an anticyclonic supercell, in the same manner as the typical cyclonic tornado, or as a companion tornado either as a satellite tornado or associated with anticyclonic eddies within a supercell. An illustration of generation of infrasound in tornadoes by the Earth System Research Laboratory's infrasound program. Tornadoes emit widely on the acoustic spectrum and the sounds are caused by multiple mechanisms. Various sounds of tornadoes have been reported, mostly related to familiar sounds for the witness and generally some variation of a whooshing roar. Popularly reported sounds include a freight train, rushing rapids, or waterfall, a nearby jet engine, or combinations of these. Many tornadoes are not audible from much distance. The nature of and the propagation distance of the audible sound depends on atmospheric conditions and topography. The winds of the tornado vortex and of constituent turbulent eddies, as well as airflow interaction with the surface and debris, contribute to the sounds. Funnel clouds also produce sounds. Funnel clouds and small tornadoes are reported as whistling, whining, humming, or the buzzing of innumerable bees or electricity, or more or less harmonic, whereas many tornadoes are reported as a continuous, deep rumbling, or an irregular sound of noise. Since many tornadoes are audible only when very near, sound is not to be thought of as a reliable warning signal for a tornado. Tornadoes are also not the only source of such sounds in severe thunderstorms. Any strong, damaging wind, a severe hail volley, or continuous thunder in a thunderstorm may produce a roaring sound. Tornadoes also produce identifiable inaudible infrasonic signatures. Unlike audible signatures, tornadic signatures have been isolated, due to the long-distance propagation of low-frequency sound. Efforts are ongoing to develop tornado prediction and detection devices with additional value in understanding tornado morphology, dynamics, and creation. Tornadoes also produce a detectable seismic signature, and research continues on isolating it and understanding the process. Tornadoes emit on the electromagnetic spectrum, with spherics and E-field effects detected. There are observed correlations between tornadoes and patterns of lightning. Tornadic storms do not contain more lightning than other storms, and some tornadic cells never produce lightning at all. More often than not, overall cloud-to-ground lightning activity decreases as a tornado touches the surface and returns to the baseline level when the tornado dissipates. In many cases, intense tornadoes and thunderstorms exhibit an increased and anomalous dominance of positive polarity, c.g. discharges 49 electromagnetics and lightning have little or nothing to do directly with what drives tornadoes. Tornadoes are basically a thermodynamic phenomenon, although there are likely connections with the storm and environment affecting both phenomena. Luminosity has been reported in the past and is probably due to misidentification of external light sources such as lightning, city lights, and power flashes from broken lines, as internal sources are now uncommonly reported and are not known to ever have been recorded. In addition to winds, tornadoes also exhibit changes in atmospheric variables such as temperature, moisture, and pressure. On June 24, 2003, near Manchester, South Dakota, a probe measured a 100 millibar pressure, hectopascal, 2.95 in Hg, pressure decrease. The pressure dropped gradually as the vortex approached, then dropped extremely rapidly to 850 bar, hectopascal, 25.10 in Hg, in the core of the violent tornado before rising rapidly as the vortex moved away, resulting in a V-shaped pressure trace. Temperature tends to decrease and moisture content to increase in the immediate vicinity of a tornado.